state as the last component of the nutrition and metabolism chapter. So there's quite a few comparisons to be made between the post-absorptive state and the absorptive state. So namely, when we discussed the absorptive state, we said that it was a series primarily of anabolic reactions. And that has a lot to do with the timing of when you're absorbing your food. So again, keep in mind that during digestion, that's when most absorption is happening. And so that's when you're actually using those nutrients to build. However, here in the post-absorptive state, you are 3 to 4 hours post a meal, and you're now seeing levels of glucose begin to drop, but those tissues that need the glucose are still going to need some source of nutrition, and so you begin to undergo catabolic reactions so that you break down all those nutrients that you just stored during the absorptive state. Again, the goal here is maintaining blood glucose levels because as those begin to drop several hours after a meal, that's when you might see things like neurons begin to lose function. So you want to maintain it somewhere here within this range. While insulin was going to be one of the main triggers of the absorptive state, here in the post-absorptive state, you see that insulin levels will begin to fall, and glucagon instead, the antagonist of insulin, will begin to rise. You also see that sympathetic stimulation of body tissues tends to have this effect. So, if you will, you could think of the absorptive state as the rest and digest period, utilizing primarily parasympathetic interactions. And sympathetic nervous system, when it kicks into gear, can override that by essentially putting you back into the post-absorptive state. And so looking here at some summaries, this is when those large form proteins, glycogen, and triglycerides would be broken down into their smaller components, hence catabolic reactions. You also see right over here that you're still maintaining glucose to make ATP. However, here we're going to see the different ways that you can use other fuels, such as fatty acids and then ketone bodies. So, of course, as we take a look here in the post-absorptive state, we see the reverse of what we saw in the absorptive state. So you can see here basically the order in which you're going to begin to break things down. So 1, 2, 3, 4, right? 5 is somewhere. Where did he go? That's it. So over here, you can actually see that we begin by, again, trying to focus on increasing blood glucose levels. So with blood glucose, the first place we go is stored glycogen. And as we saw a little earlier here in the PowerPoint, glycogen is going to be stored primarily in the liver. And we also found that it was stored in the skeletal muscles, but as we're going to see over here, we're not going to harvest glycogen from the skeletal muscles right off the bat. So first things first, glycogenolysis is the process by which we break down glycogen. If you recall, glycogenesis was how we stored it. And this is going to rely on an enzyme known as glucose-6-phosphatase. So if we take a look at this image, one that we actually saw in the earlier PowerPoint, or in the earlier slides of the PowerPoint, what we were paying attention to is happening over on this side of the diagram. What we saw during glycogenesis, right, during the absorptive state, was that blood glucose would be stored here within these cells as glycogen, and that there was an enzyme known as hexokinase that helped initiate the process. However, now that we are looking at the reverse of this action, now we're looking at glycogenolysis, so lysis means to break down. We have to take that glycogen and break it down into glucose-1-phosphate and then back into glucose-6-phosphate and then extract that as blood glucose itself. Now this relies on the enzyme glucose-6-phosphatase, and that's only produced in limited places like the liver, the kidney, and the intestinal cells. And so right here we see that step 1, glycogenolysis, begins in the liver because the liver is one of the places that we make glucose-6-phosphatase. So that's the reason this is step number 1. And of course you see that blood glucose being used here to fuel ATP production in places like the brain. So this is where it begins. However, if you still need more, then you see step 2 begin to take action, and that's actually where you begin to target glycogen stores in the skeletal muscle. So glycogen here will be broken down into pyruvic acid and lactic acids, which can then be converted into glucose by the liver. So the question is, why can glycogen here in the skeletal muscles not automatically be converted to glucose? Well, as we see here in step 2, glycogenolysis within the skeletal muscle cannot be completed due to a lack of glucose-6-phosphatase. Again, that's the enzyme that we see here that was present in the liver. So those pyruvic acid intermediates then travel to the liver, where it can utilize glucose 6-phosphatase to complete glucose formation. And then everything is fine. That same glucose can now be used to fuel ATP in cells, and it's readily accessible. So step 1, go to the liver. Step 2, go to the skeletal muscles. So step 3 is what we see whenever we're trying to burn fat. Step 3 is where you try to produce quote-unquote glucose stores by going to triglyceride or lipid storage. And as you recall here, triglycerides had 2 components. It had 3 fatty acids on a single glycerol backbone. And so the triglycerides first are extracted from places like adipose tissue, right, as well as here from the liver, as you can see, and broken into their glycerol and fatty acid components. And so if we fast forward here, what we're going to focus on is 2 things that happen. We're going to focus on how glycerol can form glucose and how the fatty acids can form ketoacids. So this process altogether is known as lipolysis, so breaking down of fats. The glycerol itself can go straight into glycolysis. And so that glycerol itself being utilized in glycolysis begins all of cellular respiration by forming your pyruvic acid, which can then move into the Krebs cycle if you have oxygen. However, what we see here is even if you can use the keto acids from the fatty acids, you do have that limiting step where acetyl-CoA formed either through glycolysis in the transitional phase or acetyl-CoA formed through the beta oxidation of fatty acids. If it can't be used, then in the Krebs cycle, then you have to convert it into another form. Now, if you'll recall, we discussed this in lecture saying that without the pickup model, right, of oxaloacetic acid, that's going to give you a situation in which you cannot use acetyl-CoA. So regardless of what the reasoning is, if you can't utilize acetyl-CoA formed through lipolysis, you convert it into what's known as a ketone body. Ketone bodies are different from keto acids. Right? This process is called ketogenesis, right? And this is done to a certain extent whenever you're trying to lose weight. So whenever you are cutting back on carbs and trying to rely on energy production through lipolysis, that's what's going to burn up your fat tissue, and you'll make those ketone bodies to a certain extent. Now, as they begin to collect, right, anytime you start to see lipolysis like this, you're automatically going to start to produce a somewhat lower pH in the bloodstream because of the acids that are associated with this. However, when you have these ketone bodies in excess, then that can lead to a condition known as ketoacidosis, and that's very difficult for the kidneys and the liver to continue to utilize, so it can be pretty damaging long term. The idea here is that these ketone bodies essentially can be used, right, although the body prefers glucose. And so we find that the brain tends to utilize the glucose for the longest amount of time. Other organs will use glucose sparing as a technique, which means they're going to be using the acetyl-CoA and the ketone bodies and amino acids first. And then after about 4 to 5 days, then the brain can begin to use the ketone bodies. And that can cause people to feel a little bit funky, essentially. So that's steps 1, 2, and 3. The last one we take a look at here is the cellular catabolism of proteins. So remember we said that proteins couldn't be stored. There was no amino acid storage break. So when we look at the catabolism here of protein, we're actually breaking down proteins that are already functional in the body, right? Maybe they are enzymes, maybe they are muscle fiber proteins like we would see right over here. Either way, the job here of this process is to break down proteins to give us amino acids. Amino acids through this beta oxidation can be converted into ketoacids, which can then be helped utilized to form glucose. So remember, ketoacids would be things like pyruvic acid and then those individual components of the Krebs cycle. Right? So we see that this process overall by which you're utilizing these amino acids going through oxidative deamination and using them as ketoacids, this is referred to as gluconeogenesis, which is a little covered up right here, but that would be the name of the process. And that literally means making new glucose. So we're making glucose substitutes here. So this is a pretty nice image. What this does is it kind of highlights for you what's happening with lipids overall. So we know we prefer glucose from glycogen, right? But when you need to utilize lipids, you can see here lipids broken down into glycerol. Glycerol is what's utilized by glycolysis to generate pyruvic acid, which then can be converted to acetyl-CoA and entering the Krebs cycle, right? Those fatty acids as well can be converted here into acetyl-CoA, which in this case is a keto acid. And again, the process by which you do that is beta oxidation. So we have glycogenolysis, we have glycolysis, we have beta oxidation. Over here, again, this is the same image that we saw earlier on, where we were actually using leftover components from these processes to store things in the form of fat, right? But now we're seeing that we reverse that. So here the triglycerides, again through lipolysis, breaking down into glycerol, fatty acids, and that glycerol, again, being used through glycolysis, fatty acids through beta oxidation being used to make keto bodies like acetyl-CoA. The nice thing about this image then is it is the only one that shows you where ketogenesis is taking place. So as a review, if you are seeing glucose, right, being derived through lipolysis, right, and that fat breakdown, you generate keto acids here. If those keto acids, like acetyl-CoA, cannot be used within the Krebs cycle because you don't have an adequate number of things like oxaloacetic acid, then that's when those are converted into ketone bodies through ketogenesis. So like we said earlier, this can be induced through hormonal regulation. The absorptive state, highly regulated by insulin, but here in the post-absorptive state, glucagon plays a pretty large role. And so we see over here an initial stimulus here in that pink box of the post-absorptive state is that plasma glucose is going to begin to drop. So again, this can just be caused by the fact that you haven't eaten in several hours. This is what's going to stimulate the release of glucagon from these pancreatic cells, right? And the overall effect here then of glucagon is that it can stimulate glycogenolysis from the liver as well as gluconeogenesis, right? Either one of those processes is going to raise blood glucose essentially, and that is going to start to maintain levels of ATP for you. Glucagon itself could also stimulate lipolysis, right, by causing fat breakdown from adipose tissue, increasing fatty acids, right, which can then be used as keto acids. Now, the time that you see this most frequently is whenever those organs are undergoing glucose sparing. So if they're trying to make sure that the brain alone is using glucose, then you have other organs like the kidneys, skeletal muscles, utilizing this particular tactic. And so overall, at the end of all of this, you can see that there's quite a bit of overlap in the chemicals we've talked about in this class and how they're associated with metabolism. So here, of course, we focus mostly on insulin, stimulating glucose uptake, stimulating amino acid uptake, right? So the idea there was that we were seeing things stored, right? Same thing over here, stimulating lipogenesis for fat storage, right? On the end of the skeletal muscle and then of the liver, we saw glycogenesis, right? But we also saw things like gluconeogenesis being inhibited. So this is going to help you store and then slow down the use of things that would otherwise be stored. That was the absorptive state. The post-absorptive state relied heavily on glucagon, so you see some antagonizing processes. Here you stimulate glycogenolysis instead of glycogenesis, right? Here you stimulate lipolysis, right, instead of lipogenesis like you did with insulin. And here you stimulate gluconeogenesis instead of inhibiting it. The overlap then comes in with some of the hormones we talked about earlier this semester. You see over here that things like epinephrine, right, and cortisol tend to have really similar effects to glucagon, right? And that makes sense because we've already acknowledged the fact that this post-absorptive state could be initiated from glucagon release as well as through the sympathetic nervous system, which relied really heavily here on epinephrine. You then see some hormones that have certain effects that tend to utilize activities that were both absorptive and post-absorptive, and that has to do with the goal of that hormone as a whole. So growth hormone, right, and thyroxine, both of those were meant to help development of tissues. And so over here you would see things like protein synthesis being facilitated by both growth hormone and thyroxine, right? Again, this was thyroid hormone. That's going to require amino acid uptake, right, for you to build those protein molecules within the cells. And what we find is that in order to build like that, you generally need to be able to metabolize nutrients. And so you see thyroxine coupled with growth hormone because thyroxine is going to help you take glucose into the cells, right, and break down glucose itself for energy so that you can do things like initiate protein synthesis. You also find that they both are going to stimulate lipolysis, right, releasing those components of fat so that you have energy, right, as well as stimulating gluconeogenesis, once again, to help find a way to gain access to nutrient reserves for energy production. So you can develop the tissues in the body, cause tissue growth with growth hormone, and thyroxine was going to help make sure that you had the nutrients intact to do that. And that is the end.